This will be fun. Try a bunch of practice problems. All right, Chem 3101. We finished the content of Chapter 10. Now we're going to take a look at some synthesis problems. And we're starting with an alkane. This is 2-methylbutane. And we want to make 2-methyl-1-butene from it. Could my students tell me, would you describe this as a Hofmann or a Zaitsev alkene, this alkene? What would you call that? Yeah, to me it looks like a Hofmann because it's not very substituted, right? We know that if you had the double bond here, right, that would be a Zaitsev alkene. Okay, I just wanted to get that out of the way first. The second thing is, and this is not a trick question, if we have an alkane as a starting material and it's non-symmetrical or unsymmetrical, what's the only possibility that I have for my first reaction? Could anybody tell me what am I going to choose as my first reaction conditions? Exactly. Somebody says bromination. Somebody says bromination with light. Absolutely. We need light to promote the homolytic cleavage of the bromine, and that is going to install the bromine at the most substituted carbon. So I end up with the bromine here. This is my alpha carbon. This is a beta carbon, and this is a beta carbon. But if we want to make the Hofmann alkene, we've got to abstract a proton from the beta carbon that I have labeled in black. So if I want to pull off this proton, this one here, am I going to use a hindered base or an unhindered base if I want to make the Hofmann alkene? What would I choose as a base here? Could anybody tell me? Exactly. Somebody says a hindered base. That person is 100% correct. Right? Somebody else says T-butoxide. I agree. Let's choose that. So we'll put here potassium T-butoxide. That works for me. Done. There we go. All right. So we were able to take this alkane and make a pretty cool alkene. Let's try the next one. You can probably guess based off of our textbook, the way he approaches problems. We're starting with the same alkane. And now we want to make the Zaitsev product. So we know that the first step, oops, that's not very pretty. There we go. We know that the first step must be treatment with bromine and light. That puts the bromine in the most substituted position, same as the last question. But now, again, we have a beta proton here, and we have a beta proton here in red. If we want to pull off the more substituted proton, or the more hindered proton, we need to use an unhindered base. Could anybody tell me a good choice of unhindered base here? And it's not a trick question or anything. Just pick your favorite one. Yeah, sodium methoxide works for me. It's the first one I saw. Let's go with that. So I'll throw in some sodium methoxide, and there we go. So what we did in the first two problems is we looked at taking that starting material and making the Hofmann alkene and making the Zaitsev alkene. So this is really cool because we were able to control the regioselectivity of where we wanted to put that double bond. We put it in the place that we want to using the correct choice of base. All right, let's try another one. This one is something that we don't look at a lot, or look at a lot of, and that is a thiol. So this is 10.23C. If we want to take this compound, so cyclopentane, and we want to make cyclopentane thiol, so with SH, really the only thing that we ever saw, the only way to make a thiol would be from the alkyl halide. So it could be the chloride or the bromide. Let's just pick the bromide for fun. And then we would treat it with NaSH. So instead of NaOH, you use NaSH. Sodium hydrosulfide is what you call that. And you can pick a solvent. So since this is an SN2 reaction, you could choose a polar A product solvent if you want, like acetone or dimethyl sulfoxide or acetonitrile. So let's just pick, I don't know, we'll pick acetonitrile as a solvent just for fun. Anyhow, so now that we know how to do that SN2 reaction, to make that thiol. So remember, this is called a thiol. It's the sulfur equivalent of an alcohol. The first thing we're going to do is we're going to halogenate that. Could we use chlorination in this case? Would that work? We know that chlorination is an option sometimes. Perfect. I saw somebody just put the thumbs up. Absolutely. You could use chlorination here. So you could use bromine and light, but since this is completely symmetrical, you could also use, I'll put here, or Cl2 and light. Either one is going to work. Let's be cheeky. Let's write the chloro in. So this is chlorocyclopentane. And now we're going to do our SN2 chemistry. That's not a very pretty arrow. There we go. So we're going to use our sodium hydrosulfide. Good nucleophile. It's a weak base. And acetonitrile, or whatever solvent you want to use. That's a polar aprotic solvent because that's an SN2 reaction. And there you go. You made yourself a thiol. Kind of interesting. Stinky. You know, thiols are very stinky, but pretty interesting. Let's take a look at 10.23D. So 10.23D. Again, all we're trying to do here is come up with efficient syntheses. So we're going to start with cyclopentane again. And now we want to make a trans diol. So we want to make sorry, I couldn't read my writing. It's a cis diol. So we want to make a cis diol. Both hydroxyls are on the same face of the molecule. Does anybody remember the conditions to make a cis diol? This is a meso compound, a cis diol. Does anybody remember the conditions for that? Kind of good review for the final exam here, trying to remember all those reactions that we looked at. It's syn dihydroxylation, that's right. What would the reaction conditions be for syn dihydroxylation? You could use that. Yep, you could use potassium permanganate for sure. That would work. Are there any other conditions that would work? Because potassium permanganate will work. Yes, Kiana, it will work. It's really strong. It's a very strong oxidizer. We'll put it in here. KMNO4, sodium hydroxide. Just put here cold. There's another set of conditions that we really liked, and that was to use a catalytic amount of osmium tetroxide, and NMO is the co-oxidant. That's another good option. Yep, absolutely. Both of those will work. And of course, to do either of those, we would need the alkene. We need to have this compound. Well, what are we going to need to do? The first thing we need to do is halogenate it. We could choose chlorine or bromine. I'll just pick bromine. And light. If you picked chlorine, there's nothing wrong with that. And now that we have the bromine, there's only one type of beta proton in here. But this is a secondary alkyl halide. So we want to minimize substitution. So we need a non-nucleophilic base. You could choose potassium T-butoxide if you want. That's so hindered. It's not a good nucleophile. That's going to give you the alkene. You could choose a DBU or DBN. That would work too. You just need a strong base that's a weak nucleophile. That's all you really need. So we're going to, we'll just use, why don't we use DBU? That doesn't get used a whole lot. So we'll put DBU and we'll put here or potassium T-butoxide. That'll work too. And then in the last step, you can choose either one of those sets of conditions. I'll just put osmium tetroxide, catalytic amount, and NMO. And we learned other methods for syn dihydroxylation. All right, we looked at a couple other ways of doing that with osmium tetroxide and a stoichiometric amount, and then sodium bisulfite in the second step, or sodium sulfite in the second step. But that's not very popular because osmium tetroxide is so toxic that using a catalytic amount is the best choice if it's available to you. All right, well, let's switch gears and look at another practice problem. And now I'm going to look at some practice problems from the back of the book. And I thought we'd get practice on a couple of resonance structures. So 10.24 just says draw Draw all resonance structures. We spent a lot of time on resonance structures in chapter 2, but those were all cations and anions. And now we're going to take a look at some radicals. We did some yesterday, but let's get a little bit more practice. We're going to try this one. And then I also wanted to try, we're going to try 2 of them. We'll try A and C. I want to leave some for you to try in your own time. There we go. So we'll try these 2. How about we start with those? All right. Could anybody tell me in the first one, 10.24a, is anybody able to just look at that and tell me how many total resonance contributors are there, including what I have in the yellow circle? There's this one plus another one, blah, 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 blah. Like, how many are there total? And it's not to fool you. If you think it's a simple answer, then it probably is. How many total resonance structures could I draw here? It's exactly. Clinton says 2 total. Clinton is 100% correct. Look, the only possibility, we have an allylic radical. Here we go. All we do is we make the pi bond here, and we put the radical down here. That's it. That's the only other possibility that there is. There is literally nothing else to draw. Done. 2 possible contributors to the resonance hybrid. What about the next one? Let's take a look. It's the same pattern over and over and over. You have an allylic radical, so we start with our arrows. We're going to make a pi bond. We take the radical, and we take one of the electrons from the pi bond, and then we're going to move the radical over, or make a radical on the carbon here, so we end up with this resonance structure that looks something like this. So now we have an exocyclic double bond like that. We have the radical here. Is there another contributor that I can draw? Sure there is. I have another allylic radical here. Let's keep going. So let's see here. Boom, we make another double bond. We make a new radical. Let's draw what that is. And we get something that looks like this. Now we have the radical over here. Are there any other contributors that I could draw here? Yes or no? Are there any other contributors that I could draw in this example? The answer would be no. That's right. That's right. My students typed it in the chat. The answer is no. There's nothing else that we could draw in this one. So there we go. A little bit of practice on those. I wanted to try another one that dealt with bond strength. So this is question 10.25. We're going to get a bunch of the suggested practice problems done today. If we have this molecule, so right here, and I'm going to label 3 protons. So I'll put a blue one here, I'll put a green one here, and I'll put a red one here. Could anybody tell me which one of these is the weakest bond? Would it be the blue, the green, or the red? Which one would be the weakest? I see some answers, but I don't see the right one. So the answer is it's going to be the green one that'll be the weakest. Okay, the green will be weakest. Why is this the weakest? It's weakest because it is allylic. It is the allylic bond, right? If you were to break that green proton bond, right, you'd end up with a radical here, and that would be a resonance stabilized radical. So that is going to be the weakest bond of all. Could anybody tell me which one of these would be the strongest bond? Would it be the blue or the red? It's going to be the red, isn't it? The red will be the strongest. Why? Because it is vinylic. If you were to form a radical there, then you have a vinylic radical. That is very disfavored. Okay, that is very high energy. A vinylic radical, not good. So there we go. Give me a thumbs up if you follow me on that now that we've gone over it. That helps, or stop me if you have a question. Everybody with me on that one? Okay, hopefully that clears up a little bit about bond strength. The next question I wanted to take a look at is kind of a weird question. It takes a little bit of scratch paper to solve this one. It's question 10.26, and it says compound A has a formula that is C5H12. Okay, it says it undergoes monochlorination to form 4 constitutional isomers. So it goes monochlorination, and you get 4 constitutional isomers. So what is the structure of A? Well, what are the possibilities for C5H12? One of them would be 1, 2, 3, 4, 5. That would be pentane. Another one would be 1, 2, 3, 4, would be 2-methyl-butane. Another one would be this, if we had 2,2-dimethyl-propane. Those are the only isomers that we can come up with for C5H12. So which one of these, when it gets chlorinated, is going to form a total of 4 constitutional isomers? If we look at the last one, this one here, if it was to undergo chlorination, it can only form one possible product. The only thing it could form is this. So just one constitutional isomer and nothing else. If you took pentane, you could end up with, so let's see here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You could put the bromine at the end, you could put it on the second carbon, or you could put it on the third carbon, like that. Those are the only possibilities for pentane. But if we have 2-methylbutane, the last one, well, how many possibilities are there for this one? If you treat this with chlorine, you can put the chlorine at the most substituted position. You could put it at one of the methyl positions. You could put it on this methylene. And you could also put it at the very end, like this. So we end up with 4 constitutional isomers. So 4 constitutional isomers. Therefore, compound A is 2-methylbutane. 2-methylbutane is compound A. Is everybody with me on that? Okay. So the next part of the question says, if you take compound A, so compound A, which is 2-methylbutane, and you treat it with bromine in light, it's going to be regioselective. Where is the bromine going to go? Is it going to go at the green carbon, at the red carbon, at the blue carbon, or at the yellow carbon? Could anybody answer that for me? Which carbon would the bromine be attached to? Yeah, it's going to go on the red carbon, the most substituted position, absolutely. So we end up with this compound. There you go. That's all there is for that one. Question 10.27, so 10.27 is another question about drawing radicals, or resonance structures of radicals. They show you this radical inhibitor called BHT. It's butylated hydroxytoluene. It's this molecule here where you have an aromatic ring with an alcohol, and then you have a tert butyl group here, a tert butyl group here, and then you have a methyl group down here. So it says, draw all the resonance structures when the hydrogen atom is abstracted from the hydroxyl in butylated hydroxytoluene, or BHT. So what happens is, when you rip this proton off, remember that the oxygen has, 2 lone pairs on it like this. So if you rip off the hydrogen in a homolytic bond cleavage, what you end up with is this radical. So let's draw the radical. You have the oxygen surrounded by 1, 2, 3, 4 electrons, and you have your tert butyl, another tert butyl, and your methyl group. So let's see if we can draw all the resonance contributors to the hybrid. We have an allylic radical right here. So we can use the same pattern that we've always used. Look, we're going to make a pi bond here. We're going to take an electron from here, to make the pi bond, and we're going to put the radical right there. So let's draw that. Going to look something like this. I didn't touch either of these bonds. There's my tert-butyl. There's the other tert-butyl, and my radical is right here. Here's my double bond to my oxygen and my methyl group. Now I have another allylic radical, so I can draw another contributor. Take my red pen. Here we go. Make a new pi bond and take this electron and put it down here by the methyl group. That's going to give me the second contributor. So let's pencil that one in. Got a double bond here, here, and here. Methyl group, tert-butyl, tert-butyl, and my radical is here. And then I have one last contributor, don't I? Because I have another allylic radical here. Zoom out. And what's that going to look like? Well, I'm going to delocalize this, put the radical up here, and that will give me the very last contributor, which looks like this. I've got the tert-butyl, the methyl, the other tert-butyl, and the radical is up here. And that's it. That's all of the contributors. So that's why BHT is so good at consuming radicals, because it becomes so stabilized when it itself becomes a radical. Remember that where the radical shows up on the aromatic ring, you always have an alkyl group, and the alkyl group serves to stabilize the radical as well. Give me a thumbs up if you think you could draw those resonance structures. Does anybody think they could draw those?
I did have a question.
Go ahead.
I know it would be the same structure as the initial radical, but would we show, like, does it have any functional purpose to show that last structure moving the radical back to the oxygen to show the
You can.
the aromatic ring completed?
Yeah, you can do it if you want, but it doesn't add anything new. So it would be identical to this one.
Okay, yeah.
All right, but there's, no harm, no foul. You can definitely do it. But I wouldn't say, if I said draw all the resonance contributors, I would not expect you to do this, to kind of complete the story. You don't have to do that. As long as you've covered them all, it's good enough for me, because you're just redrawing the exact same thing again. Cool? Does that answer the question? It's a good question. Yeah, there you go. So not necessary, but if you want to do it, hey, no problem with that whatsoever. Let's take a look at a mechanistic question. Yeah, let's take a look at a mechanistic question with NBS. NBS, we talked about it a little bit yesterday. This is question 10.28 from the book. It says, where is it? When isopropyl benzene, so this compound here is called cumene or isopropyl benzene. I like to call it cumene. The reason why is that's the common name. It's not one of the things that we ask you to memorize, but it shows up so much, especially in organic chemistry too. It's just handy to know the name. So it says when cumene is treated with NBS, so where's my NBS? N-bromosuccinimide. It says you get one product. So one product, that's going to be the benzylic bromination. So you add the bromine in the benzylic position. And then it says, what's the mechanism? Mechanism. Let's just review the mechanism of NBS bromination. So this would be benzylic bromination. Well, the first thing we need is an initiation step. Initiational. Okay. What's the initiation? It's going to be the formation of a radical from a non-radical. So when we hit that NBS with light, and let's draw the structure of N-bromosuccinimide like this. Here we go. We can even put in all the lone pairs like that. You get a homolytic bond cleavage where the nitrogen takes an unpaired electron, and so does the bromine. So that is what gives you the bromine radical. I'm just going to draw the NBS radical as well. That's doubly stabilized, of course, through resonance, but we end up with a bromine radical. So that's initiation. Now remember, once you form the radical, you have two propagation steps, You have hydrogen abstraction and halogen abstraction. So let's do hydrogen abstraction first. And that's where you remove the proton from the molecule of cumene, and you're going to remove this proton, right? Because then you're going to get a benzylic radical. And thus the bromine will come here and it's going to abstract that. So you end up making HBr and you end up making, oops, a benzylic radical. So we end up forming the benzylic radical, which looks like this, plus we also make HBr. So that's the hydrogen abstraction. Next, we have the halogen abstraction. So we'll put here halogen abstraction. Now remember that there was an ionic mechanism between HBr and NBS that produces some Br2. So there is a minimal amount of bromine in solution, but there is some, and thus the benzylic radical is going to react with that little bit of bromine. You only need one molecule for every molecule, right? So we're going to end up forming the carbon-bromine bond, and we form a bromine radical like this. So now we've got the only product we're going to make, which is this. There we go. Plus, we end up with a bromine radical. And then for termination, you can show any two radicals coming together. I don't know, let's just pick a couple here. Termination. You can show two bromines. Let's make it interesting. Let's take the cumene radical. And we'll take, you can take two cumene radicals. That's too complicated. Let's just pick a bromine radical. There we go. And then we say, okay, well, those are going to come together, just like the Beatles said, and they're going to make more of the only organic product you get from the benzylic bromination. So there you go. That's the mechanism of bromination using NBS, the initiation, propagation, and termination steps. And there you go. We provided a mechanism. Remember, the hydrogen abstraction occurs before the halogen abstraction. And remember that there's no Br2 in here, but when you form the HBr reacts with the NBS and you end up forming some Br2. But the whole idea was to keep the Br2 to a minimum so that if you're trying to do an allylic bromination with an alkene, you don't just get a bunch of addition of Br2 across the double bond. Okay. Let's see here. Let's try 10.30. Let's see here, 10.30. This is where we're taking this compound. So you'd call this ethyl benzene. It's a benzene with an ethyl on it. And it says if you take this and you treat it with NBS and light, it says you get two products. And it says identify what those products are. Okay, it says you get two stereoisomeric products of stereoisomers. Stereoisomers. If I highlight this carbon in yellow, this carbon in red, and this carbon in blue, could anybody tell me where the radical is going to be formed after I do the hydrogen abstraction? So I do the initiation, then the first step of the propagation is the hydrogen abstraction. Would the radical be where the red carbon is, the yellow carbon, or the blue carbon? Think about the last question we did. Exactly. It's going to be at the yellow carbon, isn't it? So we're going to produce this intermediate. Let me just move this out of the way. So we're going to make this intermediate, this benzylic radical, which is resonance stabilized. But remember that this carbon is treated as if it's trigonal planar. So when the halogen abstraction occurs in the next step, the bromine can add to either face of the molecule. So I could end up with the bromine coming out in front like this, or I could end up with the bromine going in back. Both are possibilities. Could anybody tell me the stereoisomeric relationship between these two compounds? How would you describe the relationship between these two? They would be a pair of enantiomers. Enantiomers.